the product construction for DFAs. I just wanted to do one more example of this, just so that we can all see it together. Hopefully you got this far in the video. The product construction for DFAs. I can see in my, I don't know if any of you use YouTube if you upload videos, but I can see like how, of course I can see how many people watch it, but I can also see the average view duration and typical, you know, these like 45-minute videos, it's like 3 minutes or something. This is just like random people on the internet who watch the videos. I don't know about all of you watching those videos since they already had some views anyway, but in case you didn't watch till the end, this was the product construction. It wasn't really at the end, I guess. The product construction for DFAs. This is, the point of this is it's how to combine two DFAs to get a, I will say, intersection or union language. Those are the intersection and the union sign. So if I have a somewhat complicated language, but I can express it as an intersection or as a union of two simpler languages, then you can kind of make two little DFAs and then like combine them together in some way to make a big DFA that does what you want. And you can do it's basically the same construction to do it with intersections or with unions. Let's just try one example. There's a fair amount of sort of formalism that we can discuss with this, but in order to do examples, you don't really have to do much formally. So let's just try one. How about I want a DFA for, this is, I guess, similar to that quiz question, but this is going to be more complicated. I would like any strings x in, I'll write AB star. I hope you remember what that star means. When I say x is in AB star, it just means x is a string using the letters A and B. So the star means the set of all possible strings using A and B. So strings x in AB star, where x has an even number of A's and ends with a B. All right? An even number of A's and it ends with a B. Now you could try to just make a DFA for this sort of with your bare hands without doing this product thing. But I think it's a little easier if you understand how to do the product construction. It's a little easier to do it that way. What that means is we have to, if we intend to do this product thing, we have to think of this big language here as either a union or an intersection of two simpler languages. Does anybody looking at this description? So the description is x has an even number of A's and it ends with a B. Can you express, is that a union of something or an intersection of something? I want to, yeah? I think it's an intersection. Yeah, how do you know it's an intersection?
Because of and.
Yeah, because of the word and, basically. You can identify this as it's this thing here and this thing here, and they're connected with the word and, which indicates that this is an intersection of two separate languages. So I'm going to think of the first one first. This would be the set of all x, where x, there's not a better way to say that, really. I suppose I didn't have to write this. X has an even number of A's. All right? This one I can make a DFA for. I'll call this like M1. And this is sort of, we have done this example before. It's sort of one of these things where the A makes it go back and forth between two states, and the B just doesn't do anything as far as those two states goes. That is to say, B just loops like that. And then the accepting state is the one on the left. So this one, it will accept if there are no A's. It will also accept if there are two A's, because then it'll go 1, 2, or 1, 2, 3, 4. So any even number of A's will be accepted here. And there could just be extra B's anywhere, all right? So that's the first machine for the first language. That's this language. And then and, it also ends with a B. So I should make a DFA for that one also. This one I could write like this. Isn't that cute? xb, where x is anything in AB star. So this says any string that looks like something followed by a b. All right. And we can similarly make a simple DFA for that. This I will call M2. And this one also I can do in two states. So it's going to look like, I thought this through before coming today. Basically, when you start, you could see A's at the beginning, which don't matter. If you see a B, though, then that should be accepted. If you see a B followed by even more B's, that should still be accepted. I'm trying to talk about strings which end with a B, right? So a single B will be accepted, or a single B followed by even more B's will be accepted. But if you see a B and maybe some more B's, but then followed by A, that should be rejected again. So it should go like this. But it's not a permanent rejection, because after you see that A, you still have a chance to finish with a B. So you can go back across. I think that's the DFA for this one. And the state on the right is accepting, because it should be accepted. Oh, my email's bouncing. Did you see that? It stopped. I don't understand how the bounces work now. I changed my email password this morning. It's probably saying my password is bad. But then it figured it out, I guess. All right. So these are my two machines. I'm going to combine them with what we call the product construction. So I'm going to give the states names just because that will help keep track of things. I'll call them ST for the first one and XY for the next one. And it's called the product construction because I want to do the product. Product in the sense of set theory, the product of two sets, the Cartesian product, you know, A cross B. So I just remembered I had a dream about that guy last night. I don't know why. He appeared in my dream last night, and it just occurs to me. I'm going to do the product construction using these two DFAs. Product in set theory means the elements of the product consist of ordered pairs from the original two things. So I'm going to take the product of the S and the T, product with the X and the Y. That means the states are going to be pairs like S. Well, I might as well just write down what the states are. There's S comma X. That's the starting state, because I take the original starting state from the first machine and pair it up with the starting state from the second machine. All right? And then I'm going to decide, what do the various arrows do from here? So this is my starting state. Where does the A arrow go? And I hope you remember how to do this. I mean, this is what was explained in the video. Where the A arrow goes, you just think about where does the A arrow go from the S, and also where does the A arrow go from the X, and that's where it goes. So from S, the A goes to T. So S turns into T, and down here, X stays as an X. So that means SX becomes TX, because the S went over to T, but the X stays here. So SX, I'll put that one here, like that. All right. What about the B arrow from S comma X? Again, you just look up here and you decide, what does the B do? S stays at S, X goes to Y. So SX becomes SY when you do B. I guess I'll put that down here. Like that. All right, and I'm going to continue drawing in the arrows. You may have to create new states as you go if you encounter states. Sometimes there are states which you never reach, and then you don't have to add them into the diagram if you don't want to. Let's do TX. Where are the arrows from here? There should always be an A arrow and a B arrow. So from TX, the A goes to S, and from X, the A stays put. So TX becomes SX, which means the arrow goes back that way. I hope everybody is with it, with what I'm doing here. TX with a B. T becomes T again, and X becomes Y. So this becomes TY, which is a new state which I haven't drawn yet. I'll put down here, like that. All right, and I need to draw, these are all the possible states, right? If I'm doing pairs of these two element sets, I'm going to get 4 possible pairs. Let's do the arrows from S comma Y. With an A, S, sorry, I have to keep on scrolling here. S goes to T, and y goes to x. So this becomes tx, which is that. All right? With a b, s comma y, s becomes s, y becomes y. That stays put, so this is a looped edge. And then finally, I need two edges from ty. With an a, t becomes s, y becomes x, so this goes to sx with an a. Sorry, I had to cross the arrows. And then ty with a b, t becomes t, y becomes y. That's a loop here. There we go. I hope I did it right. It's easy to mess up, a couple arrows here and there, but I think this is pretty good. All right. One last thing we should discuss, and that is where are the accepting states, all right? And for that, you have to sort of remember the idea of this is I'm doing the product using the intersection or the word and. It means in this diagram, we should only accept if it is accepted by the first machine and also accepted by the second machine. And that means it should only be accepted when it involves a S and also a Y. So it should look like this one is no, not that one. S and a Y, I said. This one is the only accepting state, right? That's how it's done. So this DFA apparently is one which accepts anything with an even number of A's and it ends with a B. And if you if you want to sort of check your answer, you can try it out. Like for instance, this should be acceptable here. BA should be accepted because that has an even number of A's and it ends with a B. And we can check it. Starting here, I go B, A, B, A, B, and it's accepted. So I feel good about that. All right. Any thoughts about that? One last thing to say, and then we'll move on to something different. What if it was a union instead of an intersection? You do almost exactly the same thing. We don't have to go through it again because it's almost entirely the same. Does anybody remember the difference? Yeah?
The accepting states, you would have S, comma X and T, comma Y also be accepting?
Yeah, right. So I'll try and say in words. If it's union instead of intersection, or another way to put it is if the language is described using the word or rather than and, then it's the same diagram, but accepting when I will say either the first coordinate or the second coordinate are accepting. By coordinate, I mean each of these things has a pair in it. So there's the first one and there's the second one. And if you were trying to do the union, for this example, you would choose all of the ones, so S is accepting and also Y is accepting. Now in this example, because I was doing the intersection, I took only the one with S and Y. If I were doing the union instead, I would take all the ones with a S or a Y in them, which is all except that one actually. So that would have been, like he said, this one and also SX and also TY. All right, pretty nice construction in my opinion. And I wanted to go over it just because we're going to do other somewhat similar things going forward. So this is a good sort of basic construction. There are other ways you could imagine combining DFAs together, which we're going to talk about. All right, any thoughts about that? All right, let's continue then talking about I've said several times in the past that DFAs are like not good enough to compute anything you can imagine. There are certain types of languages which cannot be the language of a DFA. Remember, a language which is the language of a DFA is called a regular language, and there is such a thing as non-regular languages. And I wanted to actually talk about a specific example of a non-regular language. Because today, time permitting, we're actually going to start talking about the next type of machine. Right? I don't know if you remember, but this course, as we go on through the semester, we're going to talk about more and more different types of increasingly complex machines and what their capabilities are. DFAs are kind of the dumbest of the batch. Their capabilities, there are many things that DFAs cannot do. So I want to talk about specific example, a non-regular language. This is one which I've mentioned before, although I want to actually explain specifically why this one is not regular. It involves this formalism stuff that we started doing last week, which is why we are capable of talking about it now. All right. I would like to show that if I call this L, say, L is not a regular language. That means, remember what that means is no DFA can have L as its language. This would have been a bogus quiz question if I asked you to give me a DFA for that language, because it is impossible. There is no such thing. But I want to explain in detail why there is no such thing. Would you mind if I write this in the style of like a proof? This is not horribly abstract, but it's hard to show that something is not a regular language because the statement is no DFA can do this. What it means, if you want to actually demonstrate that, is you have to somehow do like a proof by contradiction where I need to consider all possible DFAs and then demonstrate somehow that none of them can have L as their language. So this is going to be a proof by contradiction. So I'll start by saying something like, to get a contradiction, assume that there is a DFA. There exists a DFA M, and I'm going to write, would you mind if I write out the parts of it? Q, sigma, delta, Q0, and F. These are the 5 ingredients of a DFA. I'm going to assume there is a DFA that looks like that with the language of M equals this language here, A to the N, B to the N. All right? This is not possible, but this is how you prove that it's not possible, is by deriving a contradiction somehow from this. I hope you remember the 5 parts of a DFA. This Q is the set of states. This sigma is the alphabet, which is A, B in this example. The delta is the transition function. The Q0 is the starting state, and the F is the set of accepting states. All right. So we're going to derive a contradiction from this. Here's the idea. We consider this is going to look a little crazy, but it'll be fine. We consider this for various I. I don't know if you remember this formal description of the DFA, but the delta means what state do you end up in if you start here and then do this string in the diagram. So what I'm talking about is for various I. So this means maybe starting with I equals 1. It means if you start in the starting state and you do 1A, where does it end up? Or I equals 2. If you start in the starting state and do 2 A's, where does it end up? All right, so these things for various I, these are the where we end up after doing A to the I for various exponents, right? So after doing 1A, you go somewhere. After doing 2 A's, you go somewhere else. After doing 3 A's, you go somewhere else. And this is the key observation of the proof, which really doesn't seem like much at all, but it turns out to be super important. The DFA is finite. That's what the F means. It has a finite number of states. M has a finite number of states. And what that means is some of these, that is, these I'm talking about is where we end up. Some of them have to be the same as one another. They can't all be different. After you do 1A, or after you do 2 A's or 3 A's, They can't all be different because the DFA only has finitely many states. So some of those endpoints have to match up with one another. So some of these endpoints must be equal. In fact, infinitely many of them must be equal, but we don't care about that. Some of these endpoints must be equal. Because a DFA, that puts the F in DFA. A DFA has finitely many states. So some of these endpoints must be equal. So I'm going to say, let's say that means there's some situation must arise where it's like this equals this, right? Where you end up after doing IAs must be the same as where you end up after doing JAs for two different numbers up here, for I not equal J, right? There has to be some situations where you end up at the same place after doing different numbers of A's, all right? I hope you're still with it. We're almost done here, actually. This is kind of a clever idea. It's not an obvious way to argue this. Oh, I just saw it pop up again. And it's done again. All right. I don't understand the precise algorithm for the bouncy things. All right, some of these endpoints might be equal. Let's say that these must be the same. All right, but I will invite you to consider, but of course, the whole point of this language is that A to the I, B to the I is accepted, right? This is accepted. Because that's the definition of the language that we're talking about. It's the language of all A's followed by B's where it's the same exponent both times. And consider this, though. This right here, complicated bit of nonsense, it says after you do IAs, you end up at the same place as if you do JAs. What that means is while you're doing this string, you did IAs to begin with, and then did some other stuff. Actually, you would end up at the same point if you did the JAs to begin with and then did this other stuff, because those two, well, I'll just write that what I said and then I'll explain. This must also be accepted. Because as you're running around in the diagram, after you did that part, you end up at the same place after you did that part. So wherever you end up there, then you do B to the I, you're going to end up in the same place, so they have to both be accepted. All right? And actually, this is the contradiction, because that shouldn't be part of the language. The language is defined as A to the n, B to the n, where the two exponents are the same. And we just showed that if that is going to be in there, then also this has to be in there. And this is, it should not be in there. This should not be accepted. So this must also be accepted, but it should be rejected. Since I is not the same as J. All right? And here ends the proof. That's the contradiction. We were looking for a contradiction all along. Somewhat strange. I mean, maybe hard to hold all of this in your mind at the same time. But the point of this I will reiterate. So maybe I should write, that's the end. I like to write shewn. Because I have an old math book that writes this word at the end of all the proofs. Shewn. Yeah. Somebody in the YouTube comments complained to me once. I shouldn't say shewn. They said it's true they used to write it that way, but it was always pronounced shown, I mean. And he said it's just like the modern English word sew, like sewing clothing or something. It's written with an E, but you don't say sew, you say sew. Thank you, YouTube commenter. Anyway, what was I saying? Yeah, so A to the n, B to the n is not regular. All right. So there are languages that you can't do on a DFA. That's the whole point of this discussion here. There are many others also, although the one thing that is a little unsatisfying about this little proof that we did here is that this proof was really very specific to this language. And if I change this around a little bit, the same proof probably won't work anymore, even though maybe the thing is also non-regular. So this is not really a very general, like generally applicable way of thinking about what is regular versus what is non-regular. And we are going to come back to this in a bit of detail in a couple weeks. But I want to delay that a little bit because I want to talk about another type of machine. So this is not regular, meaning you can't make a machine that accepts this language. But of course, you know, there are fancier machines which can accept a language like that. And we're going to talk about, well, several of them over the course of the semester. But what I would like to talk about today is just a very slight variation on the DFA. And I would like to talk about what we're going to call the NFA. The F and the A are the same, but the D is replaced by N. The N stands for non-deterministic. Non-deterministic. The D of DFA stands for deterministic. The N stands for non-deterministic. And this is the difference between a DFA and an NFA is the issue of determinism. So what the determinism really means for a DFA means that when you give it the same string more than, you know, if you feed it the same string 2 different times, it's going to do the same thing both times. There's no such thing as it doesn't ever like act randomly or make its own choice while it's operating. It just does the same exact thing every time. This machine is non-deterministic, and what that means is some inputs. Can I add a word in there? How about sometimes, sorry, I'm changing my sentence a little. Sometimes the same inputs can lead to different outputs. All right. So the main sort of distinctive feature of an NFA, I will say like very specifically, i.e. something like this. This is allowed in an NFA. You could have 2 outgoing arrows with the same label. And what does the machine do in that case? The answer is like, well, it might do this one or it might do this one. That's all you can say about it. All right. Or you could imagine it's some kind of quantum multiverse where it does them both at the same time and you get 2 separate outcomes or something like that. But the same inputs can lead to different outputs. I think I meant to say outcomes. I mean, it can either accept or reject differently based on the same inputs. All right? This is called the non-deterministic. Of course, the F and the A, I might as well say, are for, as before, finite automaton. All right. So let's just look at an example, and I'll try to tell you. We'll start with drawing diagrams of everything. There is also a formal approach to this, which we'll discuss briefly, although we don't need to get too detailed about the formalism. But here is an example of NFA. How about that? This is an NFA. So in an NFA can have any number of outgoing arrows in each state. Like I said before, you could have double arrows with the same labels on them, or you can have 0 arrows. Like here, there are no outgoing arrows at all, and that's okay. You could have, you know, there could be an outgoing A but not an outgoing B or something like that. An NFA can have any number of outgoing arrows from each state. All right. So there is some kind of ambiguity. Like if you start here and I ask you, where does it end up if you read the letter B? The answer is it could go back here and end up here again, or it could go across and end up over here. Yeah?
Can you have multiple starting states?
No. This is not allowed in an NFA diagram. Yeah. Although, I think if you were to imagine an NFA concept where there were multiple starting states, it would be equivalent to these kinds of NFAs. But the ones we talk about, they always have one starting state. But if you wanted them to have more than one starting state, it'd probably be the same concept. That's a good question. I had never thought about that. Any number of outgoing arrows from each state. All right, yeah, what I was saying is, like, when you look at this diagram, I ask you, is B accepted or not? I mean, it kind of looks like sometimes it is and sometimes it isn't. But we don't like to talk about it in that way. So the definition of accepted is a little bit different on an NFA. A string is accepted when any of the possible final states are accepting. So it's a little bit harder on an NFA diagram to tell if something is accepted or not, although this one is very simple, so it's easy to tell. But a string is accepted when any of the possible final states are accepting after processing the string. So for any given string, there are many possible ways that you could follow it through the diagram. We say it's accepted if just any one of those possible ways leads to an accepting state. So in this example, is B accepted or not? The answer is yes, it is. I see a lot of nodding, which is good, usually, unless you're falling asleep. B is accepted in this example. Can we give me an example of a string that's not accepted here? Yeah. Yeah, A is not accepted because it has only one way to do it, and it does not end up in an accepting state. So here, B is accepted. A is rejected in this particular example. And there's actually another category here, at least from the point of view of the diagram. What about BA? Oh, that's not interesting the way I thought it was. BA you can do right here. BA. Okay, it's not possible on this diagram, but for some NFAs, it may be that you can't possibly even do the string at all. For example, it was like this. In this case, I could ask, is A, B accepted? What this means is you look at all possible ways to process the string A, B, and if any of one of them ends up in the accepting state, then you say it is accepted. In this case, this is like one of those weird, stupid things from discrete math about the empty set. What are all possible ways of doing A, B in this diagram? There are no such ways. Does that mean automatically the answer should be yes or no? This is a weird thing from discrete math. I think the answer should be no here, and it's because what it means to be accepted is there exists a path doing A, B in this diagram, which ends over here. And there does not exist such a path, right? Because you can't even do A at all from the beginning. So the answer is no. There is not. The time when you get an automatic yes for the empty set is when you're saying a for all about the empty set. Then anything you say is true. Like, all my ex-wives are models. This is true because I have no ex-wives. And so I can say anything I want about them. All right, and it will be true. Great, this is the basics of an NFA. Can anybody say, actually, on this one, anybody want to, can you say what's the language of this NFA? Can you describe, perhaps in words, what are all the strings which can be accepted on here? It has a fairly simple answer once you can see it. You have to kind of learn how to read these diagrams. It's different from looking at a DFA diagram.
Just start with B.
Yeah, anything that starts with a B. And actually, in my opinion, like once you get used to it, I actually find NFAs a little easier to relate to somehow. Because to me, it's very clear when I look at this. How do you get here? You got to start with B, and then you can do whatever else you want. So to me, this is a very clear diagram versus a DFA for any string that starts with B is a little bit more complicated. Yeah.
Because you technically aren't allowed to start with A, does that mean that it accepts everything that can be possibly put into it? Besides empty string, I guess?
Besides the empty string? Yeah, I suppose that's true of this one. Yeah, it's really just because, well, yeah, it's true. Although we usually are not gonna try and ask questions like that, but yeah, any string which you can fully kind of read except for the empty string will be accepted here. Yeah, it's true. All right. NFAs, generally speaking, are simpler in the diagrams at least. NFA, I will say NFA diagrams are typically simpler than DFAs that do the same thing. Sorry, I forgot to write. I meant to say this one, the language is any string starting with B. All right. NFA diagrams are typically simpler than DFAs that do the same thing. That's because, for instance, to make a DFA that does the same thing, it would have to have 3 states, I think. This would be a failure. This would be an accepting state. So this is an equivalent DFA, right? But this equivalent DFA must be more complicated. So NFAs, you can use them sometimes to simplify a DFA diagram. Write it as an NFA diagram. And they are often just easier to understand when you look at them. For example, here is just one more example here. This is a fairly complicated DFA, which in my opinion is hard to understand if you're just looking at this diagram. This is a DFA. Which accepts. It's kind of complicated. Actually, once you see it correctly, it's not so hard to say what is accepted by this DFA, but you could maybe wonder what does it take to end up here or here? You have to do it. You could do some B's at the beginning, then an A, then another A, you'd be accepted. Or you could do an A, then a B, you would be accepted. I don't know, can anybody see what?
The monitor disappeared for a second.
Oh, it's back. Didn't even notice. Anybody have an idea? I'll show you an equivalent NFA. This one, in my opinion, the NFA is much clearer. An NFA for the same thing. Once you learn to read NFAs, maybe you will agree with me that this is clearer. That's the whole thing. So these 2 diagrams are equivalent. This second one here is very nice. It's sort of a somewhat linear progression. What does it take to get here? You can do whatever you like, and then you got to do an A, and then one more thing. Anyone explain in words what kind of strings are those? They have some stuff, then an A, then one more thing. Yeah.
String that ends in either AA or AB.
A string that either ends in AA or AB. Yes, I had another way of saying that. Sounds a little simpler to me. But this is correct though. This accepts anything which ends with AA or AB. I was going to say accepts any string where the second to last letter is A. That's the same, right? It either ends with AA or AB. And you can see this very clearly on this diagram. Some stuff, then an A, then one more thing. All right? It's the same as this, although this is quite a bit more complicated in my opinion. So the NFAs are a nice type of machine, and we are going to be, talking about, so we're going to go through the same kinds of things, like if I describe to you a language, can you make me an NFA which does that language? How about, can we try the one, how about the one that was on the quiz? Was it A, B to the N, A? Was that the, I don't remember, I can scroll up. B, A to the N, B. All right, that's more or less what I said. How about an NFA for B, A to the N, B? I think this is an NFA where you can kind of just sort of read the string left to right. You got to start with a B, and then maybe have some A's, and then another B. Anyone want to suggest? You got an idea?
Do you do a starting state that only shoots out B to another state?
Okay, great. Yeah, so this is, you got to start with a B. You can't start with an A because that just doesn't go anywhere. All right, then what?
Then loop A.
Uh-huh.
And then B goes out to an accepted state.
Yes, great. Yeah, that's all there is to it. You got to start with a B. Then if you want to, you can do some A's in the middle there. And you got to do one more B. And then you're done. Yeah, this is an NFA for that language. Yes?
Is an NFA kind of like it only gives responses that are necessary and like that lead to an accepting this thing? Is that like what the NFA arrows are?
I'm not sure. Like in this case, you might describe it that way. Although, for instance, if I add, say, this here, I'm not sure. I mean, now the language is now something like A to the N, B, A to the M, B. That still fit your description? I'm not sure. You could think of it something like that. I wouldn't say this A is necessary. Like strings that are accepted can omit that if they want to. But yeah, I'm not sure exactly what you mean, but probably something like what you said is a good way of thinking about it. All right, we got 15 minutes left. I got something for you all to try. I don't know if you're ready for this. I think we can try a few. So I have 3 to try. In each case, make a NFA which will accept these languages. So this one, ABXA, that means it starts with an A, then has a B, then it has anything in the middle there, and then finishes with an A. The last one is a little strange looking. I hope you remember what the star means. The star means all possible strings using elements of this set. So what this means is all strings that you can make using A's and B squareds. You're not allowed to use a B all by itself. If you want to use a B, it has to be part of a B squared. That's what this language means. All right, see how you feel. I will walk around in a few minutes and see how you're doing.
accept it if it was BAAB, that has this.
Oh,
When I say
so
X,
B
it
can be,
might have
B's allowed to be first.
P's can be part of X,
Oh,
but it just.
in general.
Yeah, the number is in there. I guess that's legal. That looks good. No? This still does not accept B, A, B, that should be. This is correct. Because X is in theory star, that means X is in string. Like it could be very, X could be very. It needs to be something.
Okay.
My other suggestion is gonna be, you go A, you could just use one state.
Yeah, yeah.
How's it going?
I'm not fully sure. I know the first one should
Yeah,
be
that's good.
good. Second one, it took me a little bit of thinking because this will odd even root there be accepting.
This is good. I think it can be a little simpler.
I'm not sure, like if you include if X has a B, I'm not sure if it
So,
doesn't show.
yeah, it was
That's what-
ambiguous. Pay attention to this. But one thing that's definitely stricken is, an even number of A's will include 0 A's should be accepted.
Okay. So the starting state should be you're accepting one as well.
Well, it has to
Say.
be.
Or it has to include B as well. Okay.
No,
So,
it can't be.
yeah,
This is close, right?
Yeah.
Yeah, agree, right?
And we know it
How's
has
it going?
But it doesn't just have to.
All right, this is great.
Yeah.
Why can't,
I think you can do this with just, so to get even, you want this kind of back and forth with A's. All you need is that.
it's out the, is this?
I don't know.
So from there, you should use just one arrow with a B that goes to an acceptance.
B squared needs to have two of these.
Oh, yeah.
Yeah, I think they have to be consecutive.
Right, so it has to.
Yes. Okay, then we should insert the fish right there. Because that allows you to this motion is.
Yes.
Which one are you on?
I thought I got the
You can allow extra B's, like what if you wanted to do
I think I know.
extra B over this first? How's it going? That's good. Actually, can I say something about this? This one right here, X, is an AB star, it means X can be any string or A's can be just.
Oh.
You can use, How's it going? Alright. You okay? This is any string you can make out of A's, B squareds. And this would include the empty string. So I would say the first starting state should be accepted. And then set that like X always back and forth. Because this, here you could do, you could do it on the one day.
See, like A loops, so because there has to be like,
But that's the thing, so you can have just one B. You have to choose this website.
yeah, so one B goes here.
Then you have to make two A's.
Two possible. If there's one B,
You
it
wanna
can't
head
be
back
accepted.
here?
I think that's how NFA is. Yeah, that's what it
Yeah,
is.
you have two different, two different.
This is good,
I think it's like, if the possibility can be accepted, and if there's two acceptance, if there's super can be accepted. It's kind of hard to explain.
No, you-
So this isn't actually, you just use
Because X is not.
It has to be. So
I would say, I think, if you want to be able to think
So
here,
basically-
I would say make a loop there.
Like, right, yeah, like,
I mean,
like the
would
one.
that,
Okay.
are you reasonable?
What, no, so it's like,
I see what you're saying.
So
Let's talk about these since we got to go in a few minutes. Thank you for playing along. So ABXA, most people got this one. Oops. This one works very nicely for NFAs. You go A first, and then B, and then X can be any string of A's and B's, and the proper or appropriate way to model that on an NFA is to do something like this. So this means in order to get here, you have to do A first and then B, but then once you get here, you can do whatever you like, any string involving A's and B's, and then you got to finish it off with an A in order to be accepted, like so. All right, so that's how I would have done that. This is pretty much the way you should do this. There are probably other ways, but I wouldn't suggest it. All right, the next one, XB, where X has an even number of A's. I will just bring this down here. Now this question, after I wrote it, some people decided this was somewhat ambiguous. I didn't say, what is X? X has an even number of A's. What I meant by that is X could also have B's in it, but the number of A's in X is even. But it also maybe has some B's in it. Now, as I was walking around, most people interpreted this as meaning that X just is some even number of A's with no B's in it. If that was your interpretation, it would look like this. To get this evenness, even versus odd, you always want two states that go back and forth. This is an even number of A's, and then I want a B at the very end, something like this. What? This is what I meant, right? So in order to get to the accepting state here, you must do some even number of A's, and then a B at the end, and it will be accepted. Now, this is not actually what I meant by this. X has an even number of A's. I mean, there is an even number of A's in X, but it might also have some B's. How could I also allow some extra B's as part of the X? Well, this here is kind of where the X part is happening. And if I want to allow additional B's, did anybody have this interpretation? How would I allow additional B's to occur? Yeah.
Loop B's on the even A's.
Yeah. Loop B's here. And I would also put one here. That's because you could, even if you want to, put B's in between two of the A's, right? Yeah, great. This is what I intended for you to do. Although if you interpreted my X slightly differently, it might look like this, but without the B's. Any questions about that? All right, and then finally, AB squared star. This means any repetitions of, or any string which is built out of A's or B squareds. So it includes things like AA, B, B, A, because that has 3 A's and a B squared in it. Or something like AA, B, 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 A, B, B. This also can be made up of A's and B squareds, but not something like A, B, A, because that cannot be made up of A's and B squareds, because that loner B is not allowed. Anybody get this one? We got a minute left. Yeah? You have an attempt?
Yeah, I did a starting state, which is the accepting state.
Okay.
And I looped it with A, and then I brought B over to a rejecting state, and then the rejecting state also shot out a B to the accepting state.
Shout out a B. Yeah, I like this. So the way that I read this is, when you're starting off, it should be accepted from the get-go, even for the empty string, because the empty string can be written out using A's and B squareds, just none of both. Any A's that you see here are fine, but if you see B's, you got to do another B immediately in order to get back to the accepting state. Yeah, I like that. All right, much more with these next time, and we will have homework due next week. Some of it is based on this the product type stuff, and then some will be on these simple NFAs. Have a good weekend. See you next time.